Hi Math 30-2s, welcome to probability lesson 5, solving problems using tables and diagrams. At the top of today's lesson, they've been very nice to you, okay? They do a little review for you, all the important concepts and formulas that we kind of need to know moving forward here. So in the first box or rectangle there, okay, they talk about odds, and obviously the key terms there are when we're talking about odds in favor of something versus odds against, okay? And that will determine which way the ratio is being presented to you. In the next 4 rectangles, you will see the formulas for mutually exclusive, not mutually exclusive, independent, and dependent, okay? So again, like I mentioned the other day, these 4 formulas you want to label, okay, on your formula sheet, or refer to this page if that's what you prefer to do, so that you know which formulas are which, how we use them. And we even saw in last day's lesson that sometimes I need to manipulate them, okay, to find a term that may be on one or the other side of the equation. Okay, so let's get into some questions here. First one is taking a look at how we use a table. So it says the table shows how the students in a large high school generally travel to school. Complete the totals in the chart. So obviously I have to add both vertically and horizontally to get the total values in the chart. So for the males going left to right there, you're going to add 350 to 200 plus another 75. Okay, so that gives me a total of 625 in the total for males. Okay, for females, you're adding 300, 100, and 175, so that's 575. Okay, and now if I add vertically, the total for bus here would be 650. The total for car would be 375. Okay, other would be 175, and then the total going either vertically or horizontally, okay, will be 1,200. Okay, so pretty easy to start there. Now, B says how many students attend the high school? Okay, well, that's just the total number there, so that's going to be 1,200. Okay, so we get into some notation now. It says use the numbers in the table to determine, first is P of M, okay? So remember the P stands for probability, so this is the probability of M, and you see in the chart capital M is the male. So what's the probability of, in this scenario, dealing with the males? So basically, when I look at the males, okay, the total there is 625, okay, and that's out of a total of 1,200. So the probability of male is 625 out of a total of 1,200. So then, okay, I reduce that 625 over 1,200, okay, and that gives me 25 over 48. Okay, so that's the probability of male. Next, I'm going to be discussing or talking about the probability of C given that M has occurred. So again, this is from last day's lesson. This is the probability of C, which would be car, given that M, or the males, have occurred. So basically, like we discussed yesterday, this is the probability of C given that M occurred. So we're saying M has occurred. So that means that I'm dealing with then the total of 625 because the male has occurred. Now, what's the probability of selecting a car given that we're dealing with the males? Well, that's going to be 200 out of my total for this question, which is 625, okay? So 200 out of 625, okay? Reduce that, we get 8 over 25, okay? Next one, how do we read this one? This is the probability of male given that car has occurred, okay? So this is the opposite of what we just took a look at here. So this is the probability that I can select a male given that I'm dealing with the cars. So I'm dealing with the cars, okay, which is a total of 375, and the probability of selecting a male in that column is 200. So it's going to be 200, okay, that's this value here, okay, out of that total of 375. Okay, so reduce that, we get 8 over 15. All right. And the last one is the probability of M and C. So the probability that we're dealing with male and car. So we want to know where male and car overlap, and that's this 200, isn't it? So it's 200 out of the total of 1,200 students. Okay, so 200 over 1,200, reduce that to 1 over 6. Okay, so there's the first little set of calculations we have to do. Now, moving on to D, it says if a student is selected at random, determine and they want the probability, okay, that a student is female. So this is the probability of female. So again, you go across in the female row and you see the total number of females is 575, and that's out of a total of 1,200 students. Okay, so 575 over 1,200, I reduce that to 23 over 48. Okay. In the next one, what's the probability that they travel by bus? So again, you take a look at the bus column here, and you see that we have 650 students that travel by bus, and that's out of a total of 1,200 students again. Okay, so reduce 650 over 1,200, okay, and we get 13 over 24. Okay. Now the next one is female and travels by bus. Okay, so you have to find female and bus. So where do female and bus overlap? Okay, well that's the value of 300. So when you take a look at female and bus, okay, they meet at 300 there. So that's 300 students out of the total of 1,200. Okay, and that's simply going to reduce to 1 over 4. Okay, in E, it says identify the following events and determine and again, we're dealing with the probability that a female student travels by bus. So this is the way you notate it. It's the probability that they take the bus given that they are female. Okay, so that's the way I would notate that question. So the probability they take the bus given that we're dealing with females. So again, I focus on the female group here, which is a total of 575, and the number of people that take the bus in that row is 300. So it's 300 out of a total of 575, okay, and I can reduce that to 12 over 23, okay. In the second one, it says we want the probability of a student who drives to school is male. So this one, when I notate it, would be the probability that a student is male given that they drive. They're going to have to drive a car, right? So that means, okay, I focus on the cars, which is a total of 375, and if they drive, it's 200. So that's 200 out of a total of 375. So that will reduce to 8 over 15. Now, F says, are the events, the student is female and the student travels by bus, independent events? Explain. So what do I do in this case? Well, in this case, what I'm going to do is I'm going to take the formula at the top of the page that deals with independent events, and I'm going to plug the probabilities into the left side and the right side and see if they equal each other. So when I take a look at the independent events formula, okay, this one would be the probability, the left-hand side will be F and B, okay, and that's female and bus. So when I take a look at that probability, that's 1 over 4, okay? We calculated that up above. The right-hand side of the equation would be, if they're independent, the probability of F times the probability at B. So the probability of female, remember, was 23 over 48. Okay, again, calculated up above. Probability of bus is 13 over 24. Okay, again, we calculated that up above. And you multiply those together, okay, you're going to get 299. Okay, here, 299 all over 1,152. Okay, sorry that the writing there looks a little bit different than it did for the other questions. The Apple Pencil I was just using died, so I wrote that solution with my finger. Okay, it'll get better here, hopefully, moving forward with the rest of the lesson. Okay, so hopefully those calculations make sense. Okay, so from A to E, I used the chart and the totals that I had created, and in F, I used the formula from up above just to show that the left-hand side equaled the right-hand side. Okay, and now, to see if the left-hand side equals the right-hand side, and they do not, obviously. Okay, on the left-hand side, I had 1 over 4. On the right-hand side, I had 299 over 1,152. They are not equivalent to each other, so therefore those events are not independent. Okay, they're not independent, so we'd say they're dependent events. Okay. Oops. Okay, let's move to the next page. Okay, so it says using probability or a probability tree diagram, okay, or using a tree diagram to determine probability. Students were given the following problem to solve. The odds that Ava will pass the math this semester are 4-to-1 and important in favor, okay, and the odds that she will pass English this semester are 1-to-9 against, okay, so important there that the first one, the odds are in favor, and the second ratio is against. If these events are independent, determine the probability to the nearest hundredth that she will pass math firstly, or she will pass first math and English, second math and not English, and third math or English. Okay, so in part A, they say express the odds in terms of probabilities. Okay, so that's the first thing that we have to do. So the first thing is I'm going to calculate the probability of passing math. Okay, so that's just the way I'm going to write it here. So the probability of passing math here would be 4 out of 5. Now, where does that come from? That comes from up here, okay, that it was the odds in favor of her passing were 4-to-1. So she'll pass 4 times to every 1 time she does not pass. So the probability would be 4 out of 5 total times, okay? Remember, odds are always part to part, where probability is part to whole, okay? Now, the probability that she is going to pass English, okay? So again, I refer to the odds that they give me in the question, okay? But this time it was 1-to-9 against. So if I'm talking about her passing, okay, it's going to be 9 passes to a total of 10 times that she's taking English, okay? Because that was against, so it was 1 fail to every 9 passes. That's the way that ratio is reading. Now in B, it says some of the students chose to use probability formulas to solve the problem. Show this method of the solution below, okay? So what I'm going to do is I'm going to write down the formula I'm using and then obviously what it is that I am discussing, okay? So the first one would be the probability of M and E, okay? And what does that stand for? Well, math and English. That's the first question I was asked to solve. So in this question, the first thing I determine is that these are independent events, okay? So the probability of M and E then would be the probability of M times the probability of E, like that, okay? Because they're independent events, that's the formula I use. So this will be 4/5 times 9/10, okay? 36/50, reduce that, 18/25. So you can see why I determined the probabilities from up above. Okay, the second one is math and not English. So this is the probability of math and not English. Again, these events are going to be independent. So this will be the probability of math times the probability of not English. So the probability of math again was 4/5. Okay, not passing English would be 1 out of 10. Okay, so that'll be 4/50, okay, 2/25, okay, is the probability there. Okay, and then the third one, this is the probability of math or English, okay? So this time I wanted, are they mutually exclusive or not? Well, these are not mutually exclusive, okay? So then I take a look at my non-mutually exclusive formula. This will be the probability of math plus the probability of English, then minus the probability of math and English. Okay, I'm just following the formulas. So what I do here is 4/5 plus the 9/10, and then I subtract 18/25. Okay, I calculated at the beginning of this question, didn't I? Okay, so common denominator there that you're gonna have to find, that'll be 50. Add those all together and you will get 49 out of 50, and there are your probabilities. Okay, so I did that, and as the question says, that student used formulas, okay, which in this case is me calculating those for you. Hopefully that you understand the process there. Now it says other students chose to use a probability tree diagram to solve the problem. Part of the tree diagram is shown. Complete the tree diagram and determine the solution. So what happens here is the following, okay? The first thing they have is P of M. That's the probability of passing math. Okay, that's 4/5 from up above. That's 80%. Okay, that's where this comes from. That's 4/5. So if the probability of passing math is 4 out of 5 or 80%, 0.8, the probability of not passing math would have to be 1 out of 5 or 0.2. Okay, so there's two paths here that we can first do the math. I pass math, I do not pass math. That's the calculation there. And like I said, this would be 1 out of 5 if you were using fractions, okay? Now from there, you can see, okay, here they're saying you passed math, you didn't pass math. Now what do I do? Well, now in each of those scenarios, I can either pass English or not pass English, okay? So below, I'm gonna have the same two things. This is gonna be passing English and not passing English, okay? And passing English from up above was 0.9, so that means not passing English would be 0.1, okay? And down here again, 0.9 and 0.1 for passing and not passing English. So then I just follow each path to get to the end. So the first one you can see would be passing math, passing English, and that's what they calculated. The next path would be the probability of math again, but this time it would be and not English, okay, to get to that spot. So I just multiply those together, okay? So that would be 0.8 times 0.1, okay? And that's going to be 0.08, okay? The next path would be the probability of not math and English, okay? So in that case, when I follow those probabilities and multiply them together, it's going to be 0.2 times 0.9, okay, and that'll be 0.18. Okay, and the last path here would be the probability of not math and not English. Okay, so again, following those probabilities, multiplying them together, 0.2 times 0.1, okay, and that will be 0.02. So now I have all four scenarios there, okay, from my tree diagram. Okay, and you can see that those values that I calculated there will be the same probabilities that we got up above, just in B, they were in fraction form, okay, in C, I've expressed them as decimal form. Okay, so let's try that kind of idea here in class example 3. It says, in a game of field hockey, the probability that Dinos score a goal from any short corner is 1/8. Okay, and that's a probability. During the first half of a match, they are awarded 2 penalty corners. Use a probability tree diagram to determine the probability that from these 2 short corners, the Dinos will score 2 goals, 1 goal, at least 1 goal, no goals. So a lot of times when you read these questions, you get really focused on the A, B, C, and D that they're asking. We will answer all of those at the end of the question. The most important thing here is to fill out the beginning of the tree diagram. Now, remember, they get 2 of these penalty corners in a game. So the first one, I could just say this would be the probability of a goal, okay? So from the question, it says the probability of getting a goal is 1/8. So the probability of a goal on the first corner would be 1/8. The probability of not scoring a goal is therefore 7/8, okay? Remember that at each step along the way, the probabilities have to add up to 1, and that's what they're saying here in this point here. So 1/8 and 7/8, okay? That is 1 or 100%. Okay, so this route is me scoring a goal. This route is me not scoring a goal. Now, that's off the first one. Now we have a second corner that we have to take. And again, it looks very similar. The probability of scoring a goal, the probability of not scoring a goal. Okay, and the same thing happens on the second corner here, right? I could either score a goal or not score a goal. Okay, and those probabilities in this question do not change. The probability of scoring a goal would be 1/8 for both scenarios, and not scoring a goal would be 7/8 for both scenarios. Okay, now you have the 4 paths, okay, or calculations that we need to do. So that's all I do. So the first path here would be the probability of scoring a goal and scoring another goal, right? G and G, goal and goal. So that would just be 1/8 times 1/8. This time we're using fractions as opposed to decimals like above. So this is just 1/64, isn't it? Okay, 1/64. This next path would be the probability of scoring a goal and then not scoring a goal. So this would be 1/8 for the goal times 7/8 when not scoring a goal. So you multiply those together, that's 7/64. Okay, the next path in this tree diagram would be the probability of not scoring a goal and then scoring a goal. So that's going to be 7/8 times 1/8. Okay, same calculation as up above. We're multiplying the same 2 fractions together. So 7 out of 64. Okay, and the last pathway here will be the probability of not scoring a goal and then not scoring a goal again. Okay, so that's going to be 7 out of 8 times 7 out of 8. Okay, so 49 out of 64, and there you go. So now I just go ahead and I answer the questions. Okay, so what's the probability of scoring 2 goals? Okay, so for part A, 2 goals. Well, if you think about that, that would be a goal and a goal. That's this first scenario here, isn't it? That's a goal and a goal. That's 2 goals. So your probability is simply just 1 out of 64. Okay, so there's the first one. The second one says scoring 1 goal. Well, if I score 1 goal, there's 2 scenarios there, okay? There's this one and there's this one, isn't there? So what would I do with those probabilities? Well, I would add them because I could say that I would score a goal and not score a goal, or I would not score a goal and score a goal. So I take those 2 probabilities and add them together, and that would give you 14 out of 64. That reduces to 7 out of 32. Okay, so if you have to make a note there that I add those probabilities together because I have 2 scenarios, then I would do that, okay, if you think you're going to forget that moving forward. Now, at least 1 goal. So this is C, at least 1 goal. So what does that mean? Well, that means I can score 1 goal or I can score 2 goals. So there's 3 scenarios there, aren't there, where I score at least 1 goal. I score 1 goal twice and I score 2 goals once. So I add those 3 probabilities together. So there's 2 goals, there's a goal, there's a goal. So I have to add those 3 together. So 1 out of 64 plus 7 over 64 plus 7 over 64. Okay, that totals 15 over 64, and you can't reduce that. Okay, so that's it. And then the last one, pretty straightforward. D is no goals. Well, there's only one scenario where I don't score 1 goal, and that's that last one. So the probability of no goals is 49 over 64. So like I said at the beginning of the question, sometimes it's intimidating when they give us all these things to calculate. But if I just draw the tree diagram, I can answer any of those questions that they throw at me, okay? Now, in the above examples, the 2 events were independent, but a probability tree diagram can also be used for dependent events, as in the next example. So the question we just did on the scoring the goals in the game, scoring a goal or not scoring a goal in the second corner had nothing to do with whether or not I scored a goal in the first corner, right? Independent events. But as we're going to see now, we're going to use a tree diagram, and it is going to be for dependent events. Cheryl is trying to show John how to solve problems based on the following information. 2 machines, which we will call A1 and A2, produce all the glass bottles made in a factory. The percentages of broken bottles produced by these machines are 5% and 8% respectively. Okay, so again, that means 5% for A1 and 8% for A2. Machine A1 produces 60% of the output. Cheryl suggests the following strategy. First, introduce symbols to represent the information. Second, write the given probabilities in terms of the symbols. And then third, set up a tree diagram. So again, those are kind of your notes for this section. These are the steps you're going to want to do, okay, when you are trying to set up a tree diagram, whether it is for a situation with dependent or independent events. Okay, it doesn't matter. Those are always good rules to follow. So in A, what we're going to do is we're going to complete John work, which is stated or started below, sorry. Okay, so they give me the symbols that we're talking about. A1 is going to be a bottles from A1, A2 is going to be a bottles from A2, and B is going to stand for a broken bottle. Okay, so those are going to be the variables or letters we use to notate things in this question. So first thing is the probability of A1. That means what's the probability a bottle is from machine 1? Okay, well, they tell me in the question that 60% of the output comes from machine A1, so the probability then is 0.6, okay, or 60%. That therefore means because there's only 2 machines that if 60% of the bottles come from A1, 40% of the bottles are coming from A2, okay? Now, what do we have there? In the next 2, they've given me the percentages, 5% and 8%. Okay, well, where do those come from? Well, 5% is saying that the percentage of broken bottles produced by these machines are 5% and 8% respectively. So that means 5% come from A1. So this is the probability that a bottle is broken, given that it came from machine A1. The next calculation would be the probability that a bottle is broken given that it came from the second machine or machine A2, okay? So there we got to practice using some percentages, okay, in terms of probability, okay, and also notation inside the brackets there. Now, John sets up a probability tree diagram with the first branches leading to the machines and the second branches leading to the broken or not broken items. So again, as opposed to the question we did on corners, okay, where there was one corner and another corner, in this question we have two things to discuss. Which machine is producing the bottles, and then are they broken or are they not broken? So you can see at the top here, okay, this is the probability that it came from A1, 0.6. The probability comes from A2 is then 0.4. Okay, remember the percentages, or the probabilities, I should say, at each stage along the process always add up to 1, don't they? Now, the next notation there is the probability that a bottle is broken coming from A1. Well, that's 5%. Okay, so below that, the probability that it's not broken when it comes from A1 would be 95%. Remember, they add up to 100%. Now I go to machine A2. So how would I write this? Well, this would be the probability that a bottle is broken coming from A2, and this would be the probability that a bottle is not broken coming from A2, okay? So we learned that this is 8%, right? Probability a bottle is broken from A2, so that means that 92%, okay, is the probability that the bottle is not broken when it comes from A2. So we've got all of our branches, okay, filled out here. So all I do now is multiply those probabilities together. Okay, that's all I'm going to do here. So you can see in the first one, I'm going to multiply these values together. This will be 0.6 times 0.05. Okay, multiply the probabilities at each level. This is going to be 0.03. Okay, so the next one would just be the probability of A1, okay, so that it comes from A1, times the probability that it is not broken coming from A1. Okay, lots of notation here. So this is 0.6 times 0.95. Okay, so 0.57. Okay, just moving along here, this would be the probability of A2 and broken. Okay, so that's what we got there. So this is the probability that it came from A2 times the probability that the bottle is broken and that it came from A2. Okay, so this is 0.4 times 0.08 or 8%. Okay, multiply those together, you get 0.032. Okay, and lastly, this is the probability that the bottle came from A2 and it's not broken. Okay, so again, that's just the probability of A2 times the probability of not broken given that it came from A2. Okay, so this is 0.4 again times 0.92. And those will give you 0.368. Okay, so now I should be able to answer any questions that they want to throw at me here. Cheryl asked John some questions to see if he understands what he has drawn. It says, if a bottle is chosen at random, determine the probability that the bottle is that it is a broken bottle produced by machine A1. So what you're looking for is this, the probability of A1 and B, okay, that it came from A1 and it's broken. So you look up there, well, that's the first one, okay, that's right here. So this is 0.03, okay. In the next one, it says, which of the final outcomes in the diagram relate to the event a bottle is not broken? So when you take a look at all those pathways, which ones have not broken bottles? Well, A1 and not broken, okay, and as well A2 and not broken. Okay, those are the two paths. So it says if a bottle is chosen at random, determine the probability that the bottle is not broken. Okay, so if a bottle is not broken, we have two scenarios there, right? This one where we have a not broken bottle, and also this one down here. So it could be that one or the other one. So I add those together. So that's 0.57, or it could be the 0.368. Okay, so you take those together, okay, and you get 0.938. Okay, that's that. So last page here, we're basically going to be on our own a little bit more and try and solve a problem here. As part of an experiment into the learning process, a mouse is put into a maze and rewarded with food every time it turns right. If the mouse turns right, the probability that it turns right the next time is increased by 20%. If the mouse turns left, the probability that it turns left the next time is decreased by 20%. Assume that there is an equal probability that the first turn will be to the left or to the right. So lots of important information there, okay? I'm not in the write-up of the question, and we'll go back and underline and highlight stuff as we need it in when we do these calculations. So it says, let R1 and L1 represent the events. The first turn is to the right, and the first turn is to the left, respectively. So what would be meant then for R2/R1? What does that mean, R2/R1? So that means what? Okay, the mouse turns right the second time, given that it turned right the first time. Okay, so that's what that means. So we're just, if you want me to write that down, I can. Okay, so the mouse turns right, okay, the second time. Given that it turned right the first time. Okay, so that's the notation there. And what is being notated. Now, determine as an exact decimal the probability of each event. So here we go, okay? The first turn is to the right. Well, they say the last line of the whole write-up at the top says, assume there is an equal probability that the first turn will be left or right. Well, if there's an equal probability, that would be 50% or 0.5, okay? Same thing with the second one. The first turn is to the left. That's 0.5 because they said the first turn, left or right, has an equal probability. So that's 0.5 for each of those. Now, the second one, okay, here, or the third one, I guess, under B, the second turn is to the right, given that the first turn is to the right. So this is where we go to the top and we take a look at what they say. It says, if the mouse turns right, the probability it turns right the next time is increased by 20%, right? So here's the mouse turning right, okay? To that, you add 20% of 0.5, okay? Because that second turn is going to be increased by 20%. So that calculation should be 0.5 plus, and then you're going to add 0.2 of 0.5, which is 0.1. So that will give you 0.6. Now in the next one, the second turn is to the left, given that the first turn is to the left. And then the write-up again, it says if the mouse turns left, the probability it turns left the next time is decreased by 20%. So a very similar looking calculation, but this time I subtract 20% of 0.5, okay? So that is going to be 0.5 minus 0.1, so this gives me 0.4. Okay, so now it says put the probabilities in B onto a probability tree diagram, and then basically then we'll take a look at the three questions that they're asking, basically determine the probability that both to the right, both to the left, or both are different, okay? So I know that when I draw this, okay, my first calculation, okay, is gonna be talking about the first turn by the mouse. Well, they said, and I calculated above, the first turn has an equal probability of occurring, so each turn is going to have 0.5 chance, okay? So we'll say this is me going to the right, and this is me left. So the first right turn and the first left turn, okay? From there now, okay, the mouse can go one of two directions again, can't it? Okay, so then I have two choices that come from each one. Now, remember, after I go right the first time, the probability that it goes right again is 0.6. So there's the second turn to the right. That means if it's 0.6, it goes to the right, the second turn is going to be 0.4, right? Those probabilities have to add up to 1. So there's left on the second turn, okay? So if the mouse went left on the first turn, okay, again, it's going to be 0.6 for the second turn to the right and 0.4 for the second turn to the left. Okay, and there you go. You've filled out the probabilities and all the moves that this mouse can potentially make. So now I do my calculations for each pathway in this tree diagram. So the first one would be the probability of going right on the first move and right on the second move. Okay, the next one would be the probability of going right on the first move and left on the second move. then the probability of left on the first move and right on the second move, and then lastly, the probability of going left on the first move and left on the second move. Okay, so there's the notation. Multiply the probabilities at each step. So this is 0.5 times 0.6. Okay, so that's 0.3. This pathway would be 0.5 times 0.4. Okay, that'll be 0.2. Then 0.5 times 0.6. Okay, so again, that will be also 0.3. And lastly, I will have 0.5 times 0.4. Okay, again, 0.2. So now I can go and answer my questions. Okay, so the first one in I says the probability that you go both to the right. Okay, so there'll be right and then right. Well, there's only one scenario that does that. That's right here. So that probability is 0.3. Okay, there's the first one. Okay, the next one, okay, the second one is both are to the left. Well, again, there's only one that goes to the left on both moves. That's that one there, 0.2. Okay, and then the last one, okay, obviously going to be a little trickier. Okay, but the last one says that we go in different directions. So the ones that go different directions are the two middle ones, aren't they? Because it goes right and left, and then left and right. The other two moves are both right or both left. So what do I do with those two probabilities? Well, I add them because I could have the first scenario or I could have the second scenario. Okay, so the probability there is just 0.5. All right, and that's it for today's lesson, you guys. So again, as always, any questions, get a hold of me. I'll try and get back to you as soon as I can with some help. Have a good night.